So this is question 6, and here we have a 1 second delay and 10 times e to the power of minus s divided by s plus 10. Now the questions are basically find the stabilizing interval, find the stability interval using the first order Pade approximation, find the stability interval with the second order approximation, and compare the closed loop step responses. So basically this will be a quick video because I've already covered this in Q5. So there it is. We have the body plot here. We can use the body plot to exactly determine at which frequency we have the -1 crossing, and therefore the stability of the transfer function regardless of the delay. This really doesn't matter. It alters the body plot so that we have a high argument value here as omega increases. And keep in mind that this is 10 to the power of 1. If it's 10 to the power of 3, this will become more dramatically and close to minus infinity. So we are interested in the point where 180 degrees is crossed, and at that point we look at the frequency. We look the frequency up in the magnitude plot. Since, for example, if you have 20 log the gain, then you have to divide by minus 20 and then by 20 and then take the 10th power of the result, and that would give you the gain, and inversing it will give you basically the gain value, the upper bound on stability. Now we can see that line by line we can work out that at negative 180 degrees we have 0.96 as the gain value, and 1 plus kg j 2.86 equals 0 can be also written. You can also work out it yourself. Here we can see that basically these terms here cancel out, and that's also the reason why we look at e to the power of minus 180 degrees. There should be a j, by the way, here. And k equals 1 divided by 0.96, which gives us 1. Now the first order Pade approximation, which is a time domain method basically, because we use again poles and zeros. This is a frequency domain method, this is the time domain method. In the time domain we use Pade approximations. So here we have the substitution, and all you have to do is you have to substitute tau equals 1 for our case, and then you have the minimum phase part and then the delay part. So, and keep in mind that using the final value theorem, you can see that this is basically gain 1 in steady state, or also important that E has gain 1. So this is an all-pass filter, by the way. This approximation is a special approximation that has many properties that we should consider. One of them being that this is an all-pole transfer function, or not all-pole, I'm sorry, an all-pass filter, sort of. So each frequency that comes to this transfer function will be passed through. So it's not a low pass or high pass. So, and it tries to emulate the effect of delay. So yeah, we add a 0 to the right half plane, a pole to the left half plane. So, and when you use the substitution into the transfer function, you get this. Now, at this point, using basically the root locus would be a bad idea because sketching the root locus of this system and then trying to work out the gain condition, phase condition, I would not prefer it. It's up to you. You can always use that. But when you have MATLAB, it's easy. But if you don't have MATLAB, stick with the algebraic method because you have a calculator that helps you out. So here we have the direct substitution method that we've already covered, and you can see that plugging in Sj omega gives us the two equations. One of them gives us omega values, hopefully the other one gives us k values here. Now, in the body plot, we can see that the approximations have basically a different phase plot, and keep in mind that we are trying to calculate the stability interval, which is which uses the phase plot. If this is not really that correct, then how can I use this to conclude a stability interval? It's not a good idea to take the body plot of, or the body of the approximation, So if you use the approximation, stick with the time domain methods. If you use the frequency domain, why would you use the Pade approximation? So this is basically to remind you that never ever use a mix and match of frequency and time domain methods, especially for delayed systems, because it really doesn't make any sense. So avoid this. Just go with the direct substitution or root locus method if you use the Pade approximation. If not, the body plot itself also gives you basically the data that you need. So, and then when you have the second order Pade approximation, things get a bit crazier because you have a higher order transfer function for your approximation that will just have higher accuracy, but also a little bit of work to do. So the closed loop here shows neatly that the first order approximation does not even match the transients of the system at all. It has just a undershoot, and this undershoot basically wastes time. So the way of the Pade approximation, we can imagine that it tries to waste some time. So with only one undershoot, this is only the time wasted, and it doesn't even correspond to the amount of delay that we have in the system, and it tries to match the transient again. So it's quite a bad approximation for this system. It depends on the system, by the way. Now here, the second order Pade approximation has one overshoot and one undershoot, and this one wastes time. So this is TA, for example, and then we have another one, TB, and the sum of them corresponds to the so-called simulated or emulated delay. And again, the transients do not really match. So keep in mind that in terms of step response, it might be not that satisfactory, but in terms of stability intervals, if it works, then it works. So having higher order Pade approximations is possible, but you can see that the workload becomes heavier and it's not really meant for designing controllers because too many poles and zeros to handle. So yeah. So that concludes basically this question. We will continue with Q7.